Hi, in this video we're going to go over the quotient and root test for series. So the ratio test is a very useful test in determining whether a given series is absolutely convergent or not. So what we're going to do is we're going to take the limit when n goes to infinity of the absolute value of the n plus 1 term ratio with the an term. Now, we're going to assume that that limit exists. If the limit doesn't exist, then it's divergent. But if the limit exists and the number L of the limit is less than 1, then we can say that the series is absolutely convergent, and therefore convergent as well. If the limit is bigger than 1, then we can know that the series is divergent. And in case that we know that the limit is just 1, then the ratio test is going to be inconclusive about the convergence or divergence of the series, and we're going to have to use something else to test it. So now let's see some examples of the use of the ratio test. So how do you know whether to use the ratio test or not? Well, usually is because you're going to have some sort of quotient, and at the same time you're going to have things that you're not going to be able to use to manipulate with easily with a comparison, or something that you can do with integration tests. So for example, this one, n to the n over n factorial, this is very hard to compare to something. You can probably try to compare it with powers of n to the n in the start, but it's very difficult to just find out a right way to get that comparison. Obviously, it cannot be done with integration. So that's why we have the alternative of doing it with the ratio test. Now, the an term is an to the n over n factorial, clearly. And the n plus 1 term, and this is something that you got to be careful, is whenever you have n, now you have n plus 1. So here we have n plus 1 to the n plus 1 over n plus 1 factorial. A big part of the ratio test is to be actually capable of completing the ratio successfully. So we have the absolute value of an plus 1 over an, and this is going to be here limit when n goes to infinity of n plus 1 power to the n plus 1 over n plus 1 factorial over n to the n over n factorial. So a lot of the success of the ratio test is to be able to simplify. So now here limit when n goes to infinity, and we're going to do multiplication of these streams over multiplication of the middle. This is going to be n factorial times n plus 1 to the n plus 1 over n plus 1 factorial over n to the n. And so now notice that it will be nice if I can fold the powers into a single thing, so I can simplify in the limit, and that's precisely what I'm going to attempt to do. So I'm going to remove this n plus 1. And notice that n plus 1 times n factorial is just n plus 1 factorial. So I can see the top as n plus 1 factorial times n plus 1 power to the n. And so now that we have that, notice that we can very easily cancel out with the bottom, n factorial. And now we can kind of fold this into just simply having this, and now you're going to notice that this is n plus 1 over n to the n, but this can be simplified as n plus 1 over n power to the n, and that's going to be 1 plus 1 over n power to the n. Okay. In this limit, if you remember, this is going to be the number e. And so because this is the number e and this is bigger than 1, then we know that this series diverges. Okay. Now, you could potentially have said, well, this is going to be divergent anyway, because n to the n is much more larger than n factorial, and this is going to infinity. This is different from 0, and so it's divergent. Yeah, this is also true. But I'm using it as an example to just showcase how you go about doing the limit here. Now, of course, I'm not doing the all steps to prove that this limit is e. So make sure that if you don't know how to do that, then you do this as an exercise. Now let's move on to the next example. Now we have the series from n equals 1 to infinity of 3 to the 1 minus 2 to the n over n squared plus 1. Again, here we approach this in the same way. We first define what is a to the n, and then we define what is a n plus 1. And this is a big part, because doing this correctly is going to actually net you the right answer. If you make a mistake here when you're trying to write what an plus 1 is, then that's going to mess up your limit, and it's going to mess up your final result. So just be very careful here when you're doing that. So now this is limit when n goes to infinity of 3, 1 minus 2n plus 1 over n plus 1 squared plus 1 over 3, 1 minus 2n over n squared plus 1. So this transform into limit when n goes to infinity, and same thing, multiplication of the streams over multiplication of the middle. This is 3, 1 minus 2, and then minus 2. Just multiplying this here. And then times the bottom, which is n squared plus 1, over 3, 1 minus 2n, times n plus 1 squared plus 1. Now it's a matter of simplifying the limit. This is limit when n goes to infinity. Notice that I can cancel the 3 to the 1 minus 2n, and I'm going to be left with a 3 to the minus 2. So this is 3 to the minus 2 times, and then I can probably divide by n squared up and down. So this is 1 plus 1 over n squared. And then over here I can also divide by n squared. And this is going to give me 1 plus 1 over n squared plus 1 over n squared. And this is just me going very quickly over the limit again, because this is limit to the infinite. So at this point, I assume that you understand a lot of these techniques, but make sure to do it slowly if you need to actually get to this point. Now, when n goes to infinity, notice that this part goes to 0. This goes to 0. This goes to 0. So overall, I'm not going to need the limit here. So overall, this is going to go just to 3 to the minus 2 times 1 over, fortunately, 1. So this is 3 to the minus 2, which is 1 over 9. This is less than 1. And so that implies that by ratio test, then the series converges. Notice that since that has an n squared plus 1, you might be able to do this one by comparison, but it's very cumbersome, especially by the term on the top. So this is why this is a good option for this series. Now let's move on to a third example. Here we have series from n equals 0 to infinity of 2n factorial over phi n plus 1. And so at this point, you know the drill. we're going to go directly to limit when n goes to infinity of the an plus 1 over an. And this is going to be limit n goes to infinity of, we're going to have here 2n plus 1 factorial over phi to the n plus 1 over 2n factorial over phi n plus 1, phi to the n plus 1. And this can be simplified as limit when n goes to infinity 2n plus 2 factorial times phi to the n plus 1 over 2n factorial phi to the n plus 1 plus 1. So as you see me do this trick on the previous limit, you can probably guess then we're going to divide by phi to the n for these terms, and that is true. And so what we're getting here is just 1 plus 1 over phi to the n. And on the bottom for this term, we're going to get 5 1 over phi to the n. So notice that phi to the n just cancels out the phi to the n, and we're going to get 1 5 alive in there. So that's what we're going to get. Now, on the other hand, this 2n plus 2 factorial can be seen as 2n plus 2 times 2n plus 1 times 2n factorial. And so that's going to allow me to cancel out those 2n factorial factors. And so we get a limit when n goes to infinity. And now we get a factor here, which is a quadratic term. And this quadratic term is gonna pretty much drag on the rest of everything here. This is gonna grow much more faster than the phi to the n. So unfortunately, this term, this is going to become something of a quadratic term. We have 2 to the n plus 2, 2 to the n plus 1, plus same thing over phi to the n. So although this part goes to 0, this part is not going to 0. This goes to 0, this goes to 0. This piece on the top, it goes to infinity. And so because this is, of course, larger than 1, then this is going to be divergent by ratio test. Okay. Now let's take a look at another example. So we have now the series from n equals 2 to infinity, and we have a very complex arrangement here. We have minus 2 to the 1 plus 3n times n plus 1 over n squared times phi to the 1 plus n. So my instance tells me that this is going to be convergent just because the bottom is very dominant over the top. But we're going to actually take a look at that. So we have limit when n goes to infinity of absolute value of n plus 1 over an. And that's going to be equals to limit when n goes to infinity minus 2, 1 plus 3 n plus 1 times n plus 2 over n plus 1 squared phi 1 plus n plus 1 over minus 2, 1 plus 3n, n plus 1 over n squared, phi to the 1 plus n. So as you can see, this becomes very messy depending on the type of thing that you're doing. Now in here, it's just a matter of folding similar terms and simplifying. So this is going to be minus 2 to the 1 plus 3n plus 3. And this is going to be allowing me to cancel out with the bottom. Here I'm going to have the n plus 2 and the n squared times phi 1 plus n. And so on the bottom, I'm going to have minus 2, 1 plus 3n. I'm going to have the n plus 1. The n plus 1, and I'm going to have now n plus 1 square and phi to the 1 plus n plus 1. So I'll leave it in this way instead of adding, because I can cancel more easy the phi 1 plus n. So the next step, I can fold similar terms. This is going to cancel out, right? This piece cancel out with this. And here I'm just going to have minus 2 to the 3 on the top. Similar thing is going to happen with this 5 to the 1 plus n. Cancels out with this, and only 1 5 is left at the bottom. So now I have that. And this, from this similar terms, I'm just going to fold this out. And I can see this as n plus 2 over n plus 1. And I can fold this 2 together too. This is n over n plus 1 square. And now to finish this one up, I can just divide by n up and down on both of these limits. This is going to be 8 over 5 minus 8 over 5. And this is 1 plus 2 over n, 1 over 1 over n, and this is going to be 1 over 1 plus 1 over n square. And when n goes to infinity, all this goes to 0, and all this goes to 1, and this goes, well, I forgot the absolute value here, which actually matters because we have a negative number. And so now we have a over 5, which is bigger than 1. So we're actually going to have that this is divergent. So this is divergent by ratio test. So this was unexpected. I was expecting this to be honestly a convergent situation, but that's not gonna be the case. Okay. All right, so one last example. We have the n equals 3 to infinity of e to the 4n over n minus 2. Okay, in this case, my initial gut feeling tells me, hey, this factorial is growing faster than this, so this is going to 0, so maybe that's okay. But let's see what happens when we take the limit of the absolute value of n plus 1 over n. So this is the limit when n goes to infinity of e to the 4n plus 1 over n plus 1, so n minus 1 factorial over e to the 4n, n minus 2 factorial. Then again, we can flip this out. This is going to be e to the 4n plus 1, or simply e to the 4n plus 4. And then by n minus 2 factorial. And on the bottom, we have e to the 4n times n minus 1 factorial. Now, notice that we can cancel certain terms. Of course, e to the 4n gets canceled, and I get an e to the 4 here. And now this n minus 2 factorial is actually the smaller term. And in the bottom, I can see this as n minus 1 times n minus 2 factorial, since n minus 2 is less. So I can actually get this to cancel out. And this is going to be the limit when n goes to infinity of e to the 4 over n minus 1. This is a constant number, and this is going to infinity, so this is going to go to 0. And since this is less than 1, this is convergent by the ratio test. And so that concludes all the examples that I have for the ratio test.